Hello, I'm Catherine Saar, and this is the SF Pug September meetup. Before we begin, this meeting is being recorded and will be posted on YouTube afterward. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on when speaking, will be part of the recording. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we recommend, you can use the raise hand function to join the queue. If you're using an older version of the app which does not have this function, please use the chat to let the organizers know you would like to ask a question. They will then add you to the queue. The organizer will let you know when you are next in the queue so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we are monitoring during the presentation. SF Pug, Bay Area Postgres, is a PGUS affiliated user group, and I am a volunteer for PGUS. And SF Pug is sponsored by PGX, and I work for PGX. And without further ado, here is Lukas Fittl, CEO of PG Analyze, with automating Postgres index selection using constraint programming.
Wonderful. Thank you, everyone, for joining. Let me see if I can also do a screen share successfully. Let's see. Now this is where GoToMeeting crashes. No? Okay.
Hopefully not.
All right. Is that showing up successfully?
It is. Thank you.
All right. Wonderful. Well, thank you so much for making time today. So let me give you some context first. So this is a talk that I gave earlier this year at PG Day Chicago, and we've done a few more things since then on this whole topic, so I'll weave those into the talk as we go. The intent of this is to essentially share something that we've actually been working on at PG Analyze for a while, which is how to make index recommendations for Postgres in a, automatic, semi-automatic way. When we say automating here, we don't actually mean automatically create the indexes. Instead, what we mean is to what is the data we need and what is the process we could be using to automatically determine which indexes are the right fit for a given workload. And so what I'm going to share here today is essentially the technique we use in PG Analyze in production with our index advisor, which many of our customers love and use successfully. But at the end, I also have a link to a GitHub repo where you essentially see a standalone model that you could download right now, and with the other provided tool, essentially use it against any Postgres database. No need to use PG Analyze. So my intent here is not to sell you in PG Analyze, but rather my intent here is to share this technique and to specifically share how we use constraint programming to essentially achieve something where you can configure an automation process that finds things to do, things to improve on a database, specifically with indexes, because I think that's a very useful technique, and I think it's something that not enough engineers know about. And maybe this inspires you to do something in a certain way with your Postgres databases. Maybe you're just curious how specifically this works. I'm happy to answer any questions. Probably take the questions at the end. Like how it works, how we use it, what doesn't work. I'm happy to be transparent in all these things. Despite me running PG Analyze, I'm an engineer myself, so I spend a lot of time coding as well, and I've written at least some of the code of what I'm referencing here. So without further ado, let's go through our agenda. So first of all, I'll give you some context on the index selection problem and what it actually is, because that's not the term that I invented or reinvented. That's actually a more general term in database research. Then I'll talk about what the constraint programming model is for index selection that we've developed, and also what constraint programming is. Then I'll talk a little bit about how we utilize this index selection model that utilizes this constraint programming approach in practice. And I'll talk about a few advanced use cases. We're using Postgres after all, and so we can do some specific things like don't create any indexes that will block hot updates, and we can actually have an index selection model that respects these Postgres specific aspects. So to give a little bit of background on index selection itself. So when we say index selection, what we mean is we want to select which indexes to create on a given table so that the queries are fast, right? More indexes usually mean faster queries. But the write overhead is kept low, because more indexes also means each insert statement has to do more work. I referenced hot updates earlier, right? So if you have, an index on a column you're updating, you block Postgres' hot optimization. So that's, a bad thing. And so indexes can definitely be bad for various reasons. And so we have kind of this, balance we have to find between adding the right indexes so things are fast, but not adding too many indexes, because then, things are slow again because of the overhead. So really the question with the index selection problem is, which indexes should we select? Now, this is not a new problem. Back in 1971, before Postgres was even created, people already wrote about the optimization problem in the selection of secondary keys. And this is research that, there was a bunch of research activities in the 70s and 80s. Then there was, I would say, a pause. There were some commercial implementations, like SQL Server, for example, had some of the work going on there. And then more recently, in 2011, 2017, 2011, there was a paper published called Kofi, which is essentially talked about an index divisor for large workloads in the context of databases, not Postgres specific though. In 2017, Andrew Kane created Dexter, which essentially was a Ruby script that took a bunch of data from pgstat statements and made index recommendations based on that, which is, I think, a great effort. You should definitely check it out. And some of the things I'll speak to later reference that as well. And in 2020, some folks at a university in Germany did an evaluation of different index selection algorithms. And this again comes back to this term of index selection, right? So there's different ways of solving, like algorithmically solving when you're trying to find automatic, like indexes automatically for a given workload. One thing that's also interesting in the 2020 paper is that they also did an evaluation comparing machine learning-based approaches to other approaches. I think they had an integer programming approach as well, not a constraint programming approach. And at least in 2020, what they found is that machine learning actually didn't improve compared to the other approaches. That might have changed since then. But just to be clear, what we're talking about today is not machine learning. It's a deterministic approach that doesn't use neural networks or all that stuff at all. But certainly there is research around using ML for these type of problems, and there's definitely promise in that, but it's also not a slam dunk to use that either. So just for some extra context. Now, if I'm a human and I'm trying to optimize indexes, one of the ways I might do that is I could create different indexes and try them out, right? So if you today are trying to figure out for your Postgres database which index you should be using, well, first of all, you'll try to understand the queries, and then for a given query, you'll probably do something like run and explain, analyze buffers, understand what's in the explain output, come up with ideas on what's working, what's not working, create an index, drop an index, right? So a lot of the work we do today in practice when we do this as a human DBA type operator to a database is we essentially make educated guesses, we validate them using explain, analyze buffers, and then that becomes the indexes we choose. And I do think that that's a valid approach, by the way. So we're not really replacing that, but I think oftentimes this process ends up really expensive and really cumbersome if you have a lot of different queries. And so really the goal here is to give you a better starting point so that you can spend that time on the most promising index ideas. Now, because that is quite a lot of effort, what you might often do is you might just pick some indexes that seem right. And so this is one of our own internal database like tables in pganalyze called the issues table. And we actually, like over time, just added more indexes that seemed right. And the challenge, right, with this approach is for queries, actually, oftentimes this works well, but you just keep on adding more overhead because you're kind of like you have slightly different queries, and so you keep essentially addressing things as they come up. And so this, I think, is oftentimes I see in a lot of companies where, databases growing over time is like you just have, 10 indexes, 20 indexes on these, very frequently queried tables, which is a problem, of course, from an overhead. Now, one really essential aspect here when we're talking about this index selection problem is the ability to do hypothetical indexes. And Postgres itself has the ability to mark an index entry as hypothetical, meaning the planner will see it, but the executor won't use it. And so this, kind of bare bones mechanism is used by the HyperPG extension to essentially let us ask what would be the cost of a query if this index existed. Cost as an explain cost. So I can, with the HyperPG extension, actually create a hypothetical index and then run an explain, not an explain analyze, just a regular explain, and I can use that to determine what would Postgres estimate how expensive this is. Now, of course, behind the scenes, what HyperPG does is HyperPG has logic where it estimates the size of the index that is being created, right? So if you do a create index on 1 column versus create index on 4 columns, the size is going to be different. If it's a text column, it's going to be bigger versus an integer. And so HyperPG doesn't actually create the index. It just makes a guess essentially about how big the index could be. And so the cost is very much driven by that guess. So this works well for B-tree indexes, for example, but works really badly for GIN indexes because the estimated cost of a GIN index is extremely dependent on the values you're inserting, and you just can't estimate that well. So just something to keep in mind. Now, if we wanted to solve index selection, right, the simplest way we could do it is we could find all the columns we're filtering by. So if we have all the queries, right, we look for all the where clauses, essentially, all the join clauses where it's relevant. We come up with the possible indexes for these columns. Then we run each possible index for HyperPG with each of the queries. And then we select the index with the lowest cost. Right. This would be a valid approach if you have very small amounts of queries. If you have lots of queries, first of all, the problem is you have lots of different variations. And the other problem is, of course, you can't create all the indexes of the lowest costs. Now, really the problem is how do we create indexes for the whole workload, not just for a single query? Which multi-column indexes should we create, right? Especially as we're talking across multiple queries. And how do I, avoid slowing down the writes? Like how do I represent this desire to not make the database slower by my many indexes? So really the index selection problem in the workflow we can design, right, is we have a query workload. The query workload determines which indexes could possibly make sense. Then we can estimate the performance improvements for the queries. We can estimate the overhead for each index, and then we select the indexes, right? That's the rough shape of this problem. Now, one thing that we've done in our work at PGAnalyze, and which I would recommend you do, whether you're a human doing this work or you try to write a script that does this work, is you try to get away from optimizing full queries. Whilst I think there is actually a lot of value in full queries when it comes to joins, for example, it makes it really hard to reason about these things. And so what we've done is we've actually split up queries into what we call scans. Now when we say scan, we mean index scan using an index on this table. And so if you essentially make that transformation, right? So like you turn your query on 2 tables into 2 separate scans, and then for each of those tables, you do the assessment for each scan, what's the sequential scan cost, and then what's the existing index scan cost, so what's the possible index scan costs. Now, this has limitations, right? So again, if you have a join, this doesn't really work well, but it works really well if you're just looking at filter conditions, which a lot of the problem cases are. And so if you're just thinking about, how significant is a filter and what's the cost for that, that actually works pretty well. Now, again, we are using Postgres planner costs to estimate the performance improvement because those are cheap to calculate. We could, of course, create the actual indexes. That would be, much better. But that's too expensive. Also, again, just be reminded, I think people here know this, but costs are arbitrary units. They are, kind of not representing anything useful except something that the Postgres planner uses to compare plans and plan paths. And so, in a sense, you could say, they're anchored to a single read of a sequential page, which costs 1 unit, but that's about, well, assuming default sequential page costs, of course. But that's basically all you can say about them. So costs are not meaningful by themselves. They just make things more expensive that are likely more expensive in the execution. So just to show an example, if we take a query like this looks, messy, complicated. This is an actual example from our own database, and we turn this into scans. This is what, for example, we have automated. This essentially, makes this much more easily to digest than if you, as a human, were to analyze what to index. You would probably do something similar, right? Which is, what are the where clauses? What are the join clauses for each of those tables to then make an indexing decision? Now, we also need some way of saying what's the overhead for an index, right? Because we want to make sure to not create all the indexes. And so one way of doing this is storage size. So Again, HypoPG, for example, can calculate storage size. And I think it's actually a very useful way of doing it. What we found, and this is a slight variation on storage size, is that really it's the write overhead itself, like the individual writes, that are worth considering explicitly and making that a term. And so we've actually turned into what we call index write overhead as a metric, which is we're taking the size of the row, like the average width of each of the columns in the table, and then we're calculating average row size, in this case, 54 bytes. And then for the indexes, depending on which columns you're indexing, we're taking the byte sizes of these columns. This ignores, by the way, page headers and index entries and such. This just says, if you're indexing something that's very wide, right, like it's very, like here, column 3, for example, is a UID, 16 bytes. Column 1 is a text, 30 bytes, right? So if you're indexing column 1, for example, that's going to be more expensive versus column 2, which is a big end. And so we just want to represent that in this number. And so we're just saying, add up the column sizes, the average width of these columns, and then divide that by the row size. That's usually going to be a number less than 1. And so the idea is, the bigger that number, the closer it is to 1, the more that means you're essentially writing a full, like you're likely to write a full byte in the leaf page when you're writing a page to the table. This, of course, ignores various aspects like BGD duplication and such, but it's still a helpful, rough metric to say, don't index, texts, for example, if you can avoid it. Don't do multi-column indexes on multiple text columns if you can avoid it. And so that's what we've used here, and that actually works pretty well. Now, how do we use this data, right? So we have, let's suppose we have our scan costs, we have our index write overhead. What do we actually do with this? So maybe just a quick primer on optimization in general, and I'm not an expert at this, to be completely transparent with you. My colleague Philip, who wrote the model part of this, and who at PGCon 2023 was co-presenting this with me, he actually would tell you exactly how these things work, and he recently wrote 2 good blog posts on this as well. But essentially, the optimization problems is a class of research, right? So in computer science, optimization is a field of its own, and there are different ways of doing solving optimization type problems. You can use certain heuristics, or there are what are called exact methods, like integer programming, constraint programming, and such. So this is something where there are many things you can choose, and depending on what you're trying to do, one or more of these things make sense. Now, generally, the way we structure an optimization problem is we state the problem in a certain way. We have a bunch of data that essentially gets fed into a model. Now, what we mean by model here is not the same as a Gen AI billions of parameters type model. And what we mean by model here is essentially a code representation of a mathematical formula that says, optimize for this, minimize for this based on these inputs, and do this in a way that you can essentially give a solver a bunch of data and these like statements you're defining, like these aspects you're defining, and the solver essentially implements the model for you and solves the problem for you, right? So model is very different in a sense than what you would think if you think ChatGPT type models. To show you an example here, and again, I'm not the mathematician computer scientist here, I'm just representing what we're doing here, and we've written blog posts that explain some of this in more detail. But suppose we want to make the index write overhead small, right? That can be represented as a mathematical formula. You can essentially build a model with those formulas where it makes sense, and then you can translate that into code so that in this case, you can say, tell this is a constraint programming model, minimize this particular value of the data that's being passed in. And then a solver, which there's different solvers out there. We use CPSat, which is part of Google's OR tools, but you essentially just tell these instructions to a solver, and the solver is able to implement that for you. We have written a technical white paper about this, so if you're interested in the computer sciencey aspect of this, I'll post a link of the slides later, and you can, if you search for this, you can also find it. But essentially, if you're interested in the research aspect of this, this is the place to go. This is not necessarily helping you solve the practical aspect of how to use it, but if you're interested in just, what are the different aspects of how this was considered, why we use constraint programming, and such. Now, this model has a couple of things we're doing. So we have variables, which are the things we're trying to find, ultimately which indexes we're trying to select. Constraints, which are the rules we must follow, and objectives, which are the goals we want to achieve. So the solution, again, are the variables, right? So that's what the solver does for us, is finds these variables using the provided data and the provided rules and goals. Now, in the index selection model, we're essentially saying, select the indexes that like state constraints here. So for example, you could say minimize the costs and the index write overhead. I'll get to that more in a second. Because the problem is if you say minimize the costs, in a sense that's easy, right? Like if you just create all the best indexes for each of the queries, you have successfully minimized the costs. If you minimize the index write overhead, easy, just don't create any indexes. Your index write overhead is going to be 0. That's amazing, right? So in a sense, that's simple. Where it really becomes problematic is where you have this kind of, tug between, either minimize the costs or minimize the index write overhead, and you're trying to figure out, where on this kind of axis does my solution lie? Because you kind of have a conflict, right? You can't do both, you would think. And so there are different ways of doing this. Again, this is, in the field of optimization, there's lots of ways of doing this. We've actually experimented with different approaches. Again, this is where, if you're interested in why we've chosen a particular approach, I would defer you to my colleague who is more of an expert in this. But the one we have, ultimately ended up using is what's called the hierarchical optimization method. And the way that it's designed essentially is you first solve for a particular goal, and then you determine the outcome of that goal. And then, so for example, here we have first goal is minimizing the costs, meaning, minimize the costs of all the queries or all the scans. Then that gives us a value, right? For example, what's the maximum cost we saw across all the scans with the best indexes? What's, the total cost across all the queries? And so with these costs that are the hypothetical costs, we can now say, okay, let's say any valid solution that we find must at least have this good a cost, right? Now, if we just say, it must always be the best possible one, if the second goal is we minimize the index write overhead, we've kind of, biased our solution very much in this case to the right here, I guess, which is, we use the most indexes, and within that, if there's equivalent costs between two indexes, we would choose the one that has less write overhead, but certainly, we'll be biased towards lots of indexes. And so what we found, and what actually works pretty well, is we essentially give some tolerance, right? So we say, instead of, it must be the best possible value we found, it can be within X of that value, right? So if you think about this, like you're running explain, you're using hyper-PG, you're getting a hypothetical cost, maybe the perfect index, has a cost of 100, but an acceptable index might have a cost of 200, right? So you're still within, compared to sequential scan costs of 1 million or something. And so really what you're saying is, oftentimes, when you have these costs, be them hypothetical or real costs, the really bad costs are the really big ones, right? And so oftentimes, if you just select something that's a low enough cost, that's close enough to the best possible one, you essentially are still, performance-wise really good. You have a good enough index, but then your index write overhead can be kept lower because you don't have to have 5 multi-column indexes, for example. And so that's really, the statement we're making here is costs can be 10 times worse than whatever the lowest possible costs are. Which selection of indexes gives me that for as little index write overhead as possible? Let me see if I can walk through this example correctly. I remember struggling with this at PGA Chicago, but here's a second try. So our goals here are we have minimized costs with 10% tolerance, and then we have minimized index write overhead. We have on the right side here a matrix of I1, I2, I3, I4. These are the hypothetical indexes we've costed. And we have our scans, which is scan 1, scan 2, scan 3, right? So for each of the scans, you may or may not have a cost. So for example, if you look at this in S1 and I2, there is no value because presumably that scan 1, right, like that part of the query can't use that second index there. And so for some of them, we have costs, for some of them we don't. Now, the indexes also have index write overhead. So I1 here, for example, and I2, they both have an index write overhead of 3. This is for representation purposes, right? Like you mentioned me earlier saying, you saw me earlier mention index write overhead is usually less than 1 because we divide the row width of the table by the index width, so to say. And so here we're just using this for illustration purposes. But so suppose, we have index write overhead 3 for both of the top indexes and index write overhead 1 for 3 and 4, right? So index 3, index 4, they're the better indexes in terms of write overhead. But if you look at the costs, you can see that, for example, for S1, I1 is the best index, right? I1 has 4 costs, I3 has 8 costs, I4 has 7 costs, lower cost is better. So if we just optimize for the best indexes, I1 would be the best for S1. If we look at S2, it has 332 as a cost, right? So in this case, I4 would be the best one. If we look at S3, we see 458, right? So in this case, the second index would be the best one. So if we just were to optimize for the best indexes, we would have to choose these 3 here, right? Like we'd have to choose I1 for S1, I2 for S3, and I4 for S2, right? Like that's really the problem, is if you're just optimizing for the best possible case. Now, because we give the tolerance, right, we say, so the costs here for these best possible ones are 4 plus 4 plus 2, which gives us a total of 10. Now we say 10 tolerance, which means 11 total costs would be acceptable. And so because we allow that, we're essentially letting it switch to an index that's less overhead. So we still, in this case, pick 3 indexes, but we're essentially, if you see here, like for the third scan here, it's 4 costs with 3 index write overhead, or 5 costs with 1 index write overhead. And so we're essentially picking the one that has less index write overhead because of the tolerance. All right. Hopefully that made sense. This is one of the core mechanisms here in this, constraint programming design, especially the hierarchical optimization method, is you're picking these tolerances to give that little wiggle room, so to say, so that you're ultimately getting to lower index write overhead. Now, let's talk about a few ways of how this is used in practice, and these are just a few examples of different configurations that we've used over time, and essentially just to illustrate how it works. This is from a previous iteration of our in-app UI, which we ended up discarding this. So this, is no longer current, but it represents roughly the data that we have available here. So in this particular case, for example, here we have minimize total cost as a goal at the top, and we have minimize index write overhead as a goal, right? So these are the 2 goals. They're ordered, meaning we first optimize for cost, and we second optimize for index write overhead. And we have 0 tolerance on 2 of them, although really the tolerance matters most for the minimized total cost. This gives us a certain solution, right? So for this particular table, we get a certain solution of which indexes are the right ones to add to create. And so right now, on this particular table, we already had 12 indexes, and the recommendation here in this case was add 11 more indexes, which is a really bad recommendation, right? Like you don't want to have 23 indexes on the table. And that can be explained by, with this configuration we have here at the top, right? We're saying minimize total cost tolerance 0. That means just get the perfect index for each of these queries. Clearly, that's not a good choice. Now, if I add tolerance, right, meaning I'm okay to accept less than the perfect cost, we can actually see, so the goals section, like roughly in the middle of the screen, where it says goals minimize total cost achieved minimum 1.2 million, no tolerance. So all solutions must have a total cost of 1.2 million or less, versus here in this case, the tolerance of 0.1 allows us the total cost of 1.369 million. Again, it's across all the different scans here. And so you can see middle on the right side where it says scan cost, it says the scan cost that was essentially achieved in the final solution was a scan cost of 1.329 million, right? So a little bit less than that maximum that's allowed with the tolerance. And so that's really where the tolerance comes in, is essentially lets us find solutions that are better, so to say. In this case, the solution just meant, don't create any other indexes. Your existing indexes are good enough, which when I know workload well, that's actually a good thing, right? Like I made choices about these indexes before. Hopefully, I got them all. And so not getting any recommendations is oftentimes a good thing here as well. Now, let me try to explain a little bit more what we do behind the scenes. And there's different ways we've implemented this over the years. So what I show you here is what we have built as an open source tool you can use yourself. Again, even though we have a commercial offering for this, I want to make sure that what I share with you today does not require you to pay us any money. So you can just go on our GitHub on the link I have at the end of the slides and download a tool that implements this, fully open source standalone, just to show you how it works. To be clear, though, the solution we do maintain today is mainly the one that's in pganalyze. So if you want to use something in production, I would recommend using that one, just because that's how we've found it works best. So if you wanted to do this fully with regular Postgres without any like any external tool like pganalyze, what you would do, and what our lint tool, which we've published, does, is it takes PGSS statements data. Right, so PGSS statements, that's essentially your best representation of the query workload data. And it takes that data, and you then use Postgres 16's new feature for explaining generic plans, right? Because stat statements doesn't give you the actual parameter values, gives you the normalized versions. So if you have a where clause that says where x equals ABC, stat statements will turn it into x equals $1. Now, if we don't know the values, right, because we just get the stat statements data, the best way to do this is to do a generic query plan, which is the same thing that happens if you have prepared statement. There's custom query plans and there's generic query plans. Generic query plans are independent of the values. To be clear, generic query plans are oftentimes worse, right? So usually you want a custom plan, but just from the data that's available and what you can actually do in practice, when you want to analyze your whole workload, stat statements is the best data source, and that data source only gives you the normalized version of the queries without the values. And so that's why we use generic plans here. Now, we explain generic plan, we get a scan, right? So we essentially get a breakdown into, really complex queries. Here is the 10 different reference tables. And so for each of these tables, we can then know what the conditions are, either filter or index conditions. From that, we can come up with which possible indexes might make sense, kind of ignoring the current indexes, right? So we're just using the explain plan here as a way of digesting the queries into something more manageable. And then based on that, we essentially create a list of scans, we create a list of possible indexes, and then we use HypoPG to essentially just check the different where conditions, right? To say, if we're filtering for x equals $1 and y equals $2, if we create an index on x, what's the cost? If we create an index on x and y, what's the cost, right? So we're just like testing through different costing values, essentially, mainly with B-tree, although this does also work with GIST, for example. And then we feed that data to the index selection model. We've also come up here with a way of just having that controlled by what we call an index selection file. So the idea here is, how do we make sure that if you were to change the configuration, right? So the idea is, sorry, let me take a step back. The idea here is this flow here works will give you the same result for the same inputs, right? So if your stat statements data looks the same or roughly the same, you should get the same outputs from the index selection model. And so what that allows you to do is allows you to actually, instead of making ad hoc decisions about indexes, you could actually have your development team or your backend engineers, data platform team, make decisions, or at least have a starting point, decide a starting point on which databases should have which indexing strategy, right? Because your indexing strategy might be different if you have a data warehousing type database versus an OLTP database. You might want to create indexes differently. And so what we've done here with this lint tool is we've essentially given a YAML file that lets you, set the priorities for what you think, this database should prioritize, be it, the cost of a certain tolerance or the index write overhead and such. Now this gets passed to the tool, and then I don't have this here because it's logistics are a bit complicated, but essentially the idea is you, let me actually see, this is the screen share, let me see if I can go there. So you have this tool here that you can install locally, and then the idea is we can pass this, essentially we can run check, and check will essentially go to database, do the work, and then we'll give you a list of missing indexes to be found, right? So that's really the output of that tool here, is a list of recommendations based on a workload. Again, I'll include the link, I'll have it in the end as well, but you could run this today against your database based on set statements data. It would give you a list of missing indexes based on your query workload. All right. few more details, and then ready to take some questions on this. So there are advanced use cases here because, again, we're using Postgres, right? And so one of the things that we found where this sometimes falls short is sometimes you have queries that you care about more essentially than others, and you want to make sure that if you optimize only for total, right? You're saying the total cost should be a certain value. Sometimes you have the simplest case might be you don't have any filter, right? Like it's just there's no where clause, it's just sequential scan. It has to be because you're doing select count from a table. And so the problem is that sometimes these totals in a model get pulled up, right? Because the best possible cost for something that can only be a sequential scan is always going to be high. And so one thing we've done here is we've introduced what we call a rule. A rule is essentially something where you have a that's not determined by the model, right? So goal is something where you're looking at what's the best possible value we can find. A rule is essentially a fixed statement. I want this to be this way in the valid solution. And so, for example, you could introduce a rule that says my maximum per scan cost that I want to allow must be at most 100 times worse than the best possible cost. And this actually does change the outcome in that previous selection we ran here. So now this does actually recommend more indexes. The reason it does that is because now the total doesn't actually change much, but the individual scans do. And so this is something that we found in our what we have people use today as part of Index Advisor and PGL is actually something that includes these rules to optimize the per scan costs. And so that's something that I would recommend you look at as well, is essentially that trade-off between optimizing for a total number across everything versus individual scans or queries. The other thing we've done is we've looked at hot updates. So I'm very sure you're familiar, but maybe folks listening to the recording are not. So hot updates in Postgres, aka heap-only tuples. So it's essentially reducing update overhead by not updating index entries, right? So if you update a column in Postgres, usually the indexes also have to be updated. But if the columns being updated are not indexed, then you can essentially skip that with a few caveats, but in many cases. And so it reduces future auto vacuum effort because some of the work that auto vacuum has to do can now happen when the table is accessed, when that page is accessed, and Postgres can actually clean up some of these dead tuples. In the case of if it's a hot chain, can actually clean that up when it accesses it, right? Lots of details to this, but the point is, if you're doing really update heavy things, you really don't want to index the columns if you can avoid it. And really, if you suddenly create an index on these unindexed columns that get updated a lot, then the update statements will get slower. Now, there's an exception to this as of Postgres 16, which is Brin indexes are no longer considered to interfere with hot updates, which is a welcome improvement because of the way how Brin is, only approximating which entries exist in a table or an index. It's not essentially considered to be a problem if there's a Brin index. But yeah, still, it's like most of the time you don't have Brin index, you have B trees, and B trees you really want to avoid creating on these columns being updated. And so we can represent that, right? Like this information, you can collect the data, and then we can represent it in a model. And so we essentially introduced an additional value that's being considered for each of the indexes, which is each of the indexes, what's the hot update overhead it would have if it were to be indexed. And so we can say, here in this case, with this current solution, there is a certain number of non-hot updates that could be impacted. If we introduce this minimize update overhead goal, we can actually guarantee that that's not a problem. And again, you might actually want to increase tolerance here, though, right? Because the problem, of course, is I've seen workloads where this is not clear, where you might want to have. You might want to accept the update overhead because you just need something indexed, right? And so this is where it kind of comes back to what workload do you have, and if it's really write heavy, you might want to treat it differently than if it's read heavy. And I think the last thing I want to touch on, and this is something where we're still very much doing active work on, because I think where things really get interesting is when you're saying, well, either you can say, let me fully automate indexing with this, which we've done some experience. We have some of our customers that are, doing some work in that area with us together. But the truth is today, I wouldn't use this for automating indexes completely, right? It's just have it create index automatically. I think that's just not there yet. A related topic, though, is consolidating indexes. So if I have, 11 indexes, can I reduce my 11 indexes to less indexes, right? Like have 5 or 8 indexes. And we can actually use the index selection model to do this, right? The index selection model can like decide, which indexes may be a good fit to be replaced. It's still very risky, right? So this is the kind of thing where we have this currently in pgAnalyze as an early access feature. We've gotten a bunch of feedback. We're iterating on that. The truth is that you're very much dependent on how good your costs are, because again, they're hypothetical costs. But what we can do, just to illustrate, how this works when it does work, is suppose here we have 12 indexes. Let's say, can we reduce this down to less than 5 indexes, right? And so we can rerun the model and say, at most, allow 5 indexes, allow consolidation and removal of indexes, and you will get a result like this here, which says, add 3, remove these, I think 8 here. And really the way this works, right, is we're just recalculating it. We're saying, can we achieve our goals, right, with these constraints in place? Now, if you have a fixed rule, like maximum number of indexes 5, that takes precedence over the goals, right? So you essentially have rules go first, goals go second. And so sometimes, if you have multiple rules that can conflict, like just to illustrate this, if you have this maximum per scan cost rule, which we usually recommend putting in place, and you combine that with only have 5 indexes, then there might sometimes not be valid solutions, right? So essentially the problem here is that combining multiple very strict things might not have the outcome you hope, because it might just be impossible to have that result. But so yeah, essentially we can, come up with a solution that, is better in some ways, but is worse in others. So for example, here, the scan cost went up, but the number of indexes clearly went down, and the index write overhead went down, and the update overhead went down as well, right? So that's really the premise here of using a model, is that we can actually find those opportunities. For context, one of the things we're doing right now to make this more production ready on the consolidation piece is we actually have some goals where we're trying to say minimize the amount of change, right? So essentially, because the problem with this is it might just give you a really long list of things to change. And, to be honest, if I'm, using a tool and it tells me change these 5 indexes, that's usually not a great thing. But if it tells me, hey, there's 2 indexes and replace it with 1, that oftentimes, ends up being a reasonable choice. And so really that's where we're taking this, is essentially making smaller step incremental changes and giving you a more clear way of validating those changes. Because I do think that's, one of the opportunities here is, application engineers just over-index, and then you're stuck with, 20 indexes, and there's a question, well, which ones do we remove? What is safe to change? And I think working with data at scale like this is actually a good way to approach that. To close, in summary, what we're trying to do here, right, with this work, and why I'm sharing this, because I think, this is something that I would like to see in the world in whichever shape or form, and we're doing the work to get that in place, is we want to semi-automate index selection based on application developer and data team intent, right? So there's, different motivations from different people, but ultimately, the idea is that, doing back of the napkin type analysis only takes you so far, and big databases, it just doesn't really work that well. We want to provide explanations for why indexes were chosen, right? So we want to make it easy to introspect, overwrite this logic, configure it. Let you, define multiple conflicting objectives, like index write overhead, hot update overhead, and such should be considered. And then really what we found is that this actually works pretty well for checking for missing indexes. There are definitely cases where it doesn't work well, but it is better than not having anything. And, we think that with, improving the data quality and, improving just from everything mentioned, we can actually get this to the point where it's used successfully for consolidating indexes, and then in some cases also be used for actually automating index creation as well for certain workloads. That's all I had. If you are interested in what we're doing, we have a soon to be weekly again, starting this week, YouTube series called 5 Minutes of Postgres. My apologies, where if I don't lose my voice, you'll hear me talking about what's new with Postgres. That's really just meant as a way to highlight all the great work that people in the community are doing. So just search for pgAnalyze on YouTube, subscribe. You're going to hear me talking about Postgres for 5 minutes. And then if you want to try out the code of what I showed you here today, there's a fully working open source tool that we've built here called the pgAnalyze lint tool. that uses an open source version of the model you can also use. And then one more thing I'll mention is we actually have 2 blog posts we published. One that is a practical introduction to constraint programming using CPSet and Python that walks you through how to, actually write stuff that a solver runs. This here has, essentially a simple problem that's not a Postgres problem in the first series of the post. And in the second post, we actually give examples of Postgres index selection. So if you just want to, get going, try this out yourself, how this stuff kind of works, I would recommend you take a look at these blog posts. I think people liked them when we published them earlier this summer. But yeah, with that, I am ready to take some questions if there are any.
All right, do we have any questions? Let's see. Don't have anything in the chat. No questions? That was a really good talk, Lukas.
Thank you.
Very, very concise, a lot of good information. It even made sense to me.
Cool. Well, I'll wait one more minute if there's more questions. Otherwise, feel free to, again, ping me if you're interested to talk more about this. This is most likely the last time I'll give this version of a talk because we have some changes that we've been making. So you had the honor of seeing this talk for a last time. And then this is very much, still what we find to be valuable though, right? It's like, again, this works well in practice. So if you're at all interested in using this in your own databases, let me know. And I'm happy to, share more about that behind the scenes of how it works. Or if PGanalyze could be useful in one of your databases, let me know as well.
Perfect. Thank you so much. It looks like you've given people a lot to think about, and it doesn't look like there's anything in chat, and no one has raised their hand. So I'm going to go ahead and wrap things up. Thank you again, Lukas. Great talk. Thank you to PGUS and PGX for sponsoring. SF Pug, our next one is Tuesday, October 8th, leveraging a PL REST extension to protect sensitive data in PostgreSQL with Rajan Palanoval. Our upcoming conferences are PGConf NYC, September 30th through October 2nd in New York City, and PGEU coming up October 22nd through 25th in Athens, Greece. We will send a link by email when the video is ready, and watch our social media. You can find us on Twitter, LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are looking for speakers for 2025, so if you or someone you know is interested, please contact us. Thank you everyone for showing up. Thank you again to Lukas. Hope everyone has a great day, and we will see you next time.